Welcome to the Quiet Perspective. Tonight, you are a marine biologist. You work aboard a research vessel studying ecosystems that exist far below sunlight. Marine biology is not a single discipline. It is a convergence of oceanography, ecology, chemistry, geology, and data science. The field exists because the ocean covers more than 2/3 of the planet, yet much of it remains less observed than the surface of the moon. A marine biologist studies living systems in saltwater environments, from coastal estuaries to abyssal plains. The work is structured, measured, and patient. The ocean is not uniform. It is divided by temperature gradients, salinity layers, pressure zones, and currents that move across basins over months and years. Life adapts to each of these conditions differently. A coral reef functions as a dense biological city. The open ocean is sparse and widely distributed. The deep sea is cold, dark, and shaped by pressure that increases with every meter of descent. Marine biology, as a profession, is built on observation before interpretation. Data precedes theory. Samples precede conclusions. Most days are not dramatic. They are procedural. Field research defines the difference between theory and practice. In controlled laboratory settings, variables are isolated. At sea, variables interact. Wind alters surface conditions. Currents displace plankton blooms. Equipment must function despite corrosion, humidity, and movement. Fieldwork demands repetition and calibration. You board the vessel not as an explorer, but as a researcher. Equipment cases are secured with straps. Metal surfaces show wear from salt exposure. Labeled containers indicate preservation fluids, sediment tubes, sampling nets. Nothing is improvised. Everything is catalogued. Marine biologists often specialize. Some focus on microbial life suspended in water columns. Others study benthic organisms that inhabit the ocean floor. Some analyze fish migration patterns through acoustic tagging. Others concentrate on coral bleaching and temperature anomalies. The field expands as technology improves. Before departure, research objectives are defined. A cruise plan outlines coordinates, sampling depths, equipment deployment times, and contingency protocols. Satellite data is reviewed. Historical datasets are compared. Weather models are checked for variability. Marine biology operates within institutional frameworks. Universities, research institutes, environmental agencies, and private foundations fund expeditions. Grants determine timelines. Data collection must align with reporting standards. Observations are recorded in standardized formats to allow long-term comparison. The ocean is not static. Seasonal cycles alter nutrient distribution. Climate systems affect upwelling zones. Human activity introduces pollutants, plastics, and chemical runoff into coastal regions. A marine biologist does not work in isolation from these forces. Research contributes to broader environmental assessments. You review the mission brief inside the vessel's main laboratory. Sampling targets are listed by station number. Each station corresponds to a specific depth and coordinate. Instruments must be calibrated before deployment. Sensors measure conductivity, temperature, and depth simultaneously. These variables define the structure of the water column. Marine biology requires patience with scale. Some processes unfold over decades. Coral growth rates are measured in millimeters per year. Deep-sea sediment accumulates gradually, preserving microscopic traces of historical ecosystems. Understanding these systems requires careful, repeatable measurement. Field research also involves physical routine. Equipment must be rinsed with fresh water after exposure to salt. Filters must be replaced. Data logs must be duplicated. Digital backups are stored separately. Redundancy is built into every step to prevent data loss. You stand on deck as the vessel clears the harbor. The coastline recedes gradually. Research vessels are not luxury ships. They are functional platforms designed to carry laboratories into open water. Space is limited, Surfaces are reinforced. Storage compartments are labeled. Marine biology is defined by preparation. Once at sea, conditions may not allow for correction. Weather shifts can delay deployment windows. Mechanical failure can shorten expeditions. Every checklist completed before departure reduces uncertainty later. Below the surface, light diminishes with depth. Photosynthetic organisms occupy only the upper layers where sunlight penetrates. Beneath that boundary, ecosystems rely on alternative energy pathways. Organic matter drifts downward from surface productivity. In certain regions, hydrothermal vents provide chemical energy independent of sunlight. These are not distant abstractions. They are measurable systems. Temperature changes are recorded in decimal precision. Salinity variations influence density and circulation patterns. Pressure increases approximately 1 atmosphere every 10 meters. At 1,000 meters, the environment exerts forces far beyond surface conditions. Marine biologists learn to think in gradients rather than categories. Surface and deep are not separate worlds. They are connected by movement. Nutrients cycle. Organisms migrate vertically. Carbon transfers between layers through biological processes. You enter data into a digital log before the first station is reached. Time, latitude, longitude, sea state, wind speed, accuracy matters. Small deviations can alter interpretation months later during analysis. The profession does not rely on spectacle. It relies on consistency. The ocean appears uniform from a distance, but each sampling point reveals variation. Marine biology is the discipline of documenting that variation without assumption. The vessel continues toward open water. Instruments remain secured until the first deployment site is reached. The mission will proceed station by station, measurement by measurement. For now, the work is defined by readiness. The first sampling station is scheduled for early evening. Until then, preparation continues without urgency, but without pause. Research vessels operate on quiet efficiency. Tasks overlap. Crew members move between navigation consoles and equipment racks. Communication remains brief and precise. Marine research depends on instruments more than intuition. On deck, the CTD rosette is secured in a metal frame. CTD stands for conductivity, temperature, and depth. Together, these measurements describe the physical structure of seawater. Conductivity provides salinity. Temperature defines density layers. Depth confirms vertical positioning. Around the circular frame, Niskin bottles are mounted. These cylindrical containers will close at predetermined depths to capture discrete water samples. You inspect the seals along the bottles. Rubber gaskets must be clean. Salt residue can compromise closure. Each bottle is numbered. Each number corresponds to a depth in the sampling plan. The system is not improvised. It is mapped in advance. Nearby, plankton nets are arranged on a reinforced table. The mesh size determines what organisms will be collected. Fine mesh captures microscopic plankton. Wider mesh collects larger larvae and small crustaceans. Nets must be rinsed and checked for tears. Even minor damage can distort results. Marine biology at sea is a balance between mechanical reliability and environmental unpredictability. Equipment must perform under motion. Even moderate swells alter deck stability. Anti-slip surfaces reduce risk. Metal fixtures are bolted down. Lines are coiled and secured. You confirm battery levels in portable sensors. Redundancy is routine. Spare data loggers are stored in waterproof containers. Calibration checks are recorded before deployment. Temperature probes are compared against reference readings. Deviations are noted. In the laboratory space just inside the deck entrance, glassware is secured with elastic straps. Sample labels are prepared in advance. Waterproof markers are used. Ink must resist moisture and time. Each label contains station number, depth, date, and sample type. The vessel's navigation system marks the approach to the first coordinate. GPS accuracy is within meters. Ocean currents may still shift the ship's position slightly during deployment. Thrusters compensate when necessary. Marine biology does not operate at random locations. Sampling stations are selected based on historical data, satellite imagery, or specific research questions. In coastal regions, nutrient influx from rivers may alter plankton density. In open ocean regions, convergent zones can create biologically active corridors. You review the depth profile for the upcoming station: surface layer, thermocline boundary, mid-water column, near-bottom sample. Each layer reveals different characteristics. Surface waters may show oxygen saturation. Deeper layers may display reduced oxygen concentrations. Wind speed is recorded. Cloud cover is noted. These variables affect surface mixing and light penetration. Even small changes can influence biological distribution. The deck crew prepares the winch system. Steel cable is threaded through a guide pulley. The CTD rosette will descend vertically through the water column. The winch operator monitors tension and descent speed. Controlled lowering prevents turbulence that might disturb measurements. Before deployment, a short systems check is conducted. Communication between bridge and deck is confirmed. Depth targets are reviewed aloud. When the rosette enters the water, there is no dramatic moment. It is lowered steadily, instrument lights visible beneath the surface for a few seconds before disappearing. You monitor the data feed inside the lab. As the rosette descends, live graphs display temperature decline. Salinity shifts slightly with depth. Pressure readings increase predictably. The descent is not theatrical, it is incremental. Marine biology depends on patience during these intervals. The rosette may take several minutes to reach target depth. During this time, no adjustments are made unless readings indicate malfunction. Observation precedes reaction. At predetermined depths, electronic triggers close individual Niskin bottles. A soft signal confirms closure. Each captured sample represents a specific vertical layer. This vertical structure is fundamental to understanding ocean processes. Outside, deck surfaces glisten with spray. Salt water evaporates, leaving fine residue. Equipment is rinsed after retrieval to reduce corrosion. Maintenance is not separate from research. It is part of it. You prepare filtration apparatus in anticipation of water samples. Filters are weighed before use to measure particulate matter later. Pumps will draw measured volumes through membranes. Each step is timed and recorded. The vessel maintains position over the sampling coordinate. Minor adjustments compensate for drift. The ocean surface appears uniform, but the vertical profile below is layered and dynamic. Inside the laboratory, fluorescent lighting remains steady. The environment is controlled, in contrast to the open deck. Here, measurements are transcribed into digital logs. Backup copies are stored immediately. When the rosette returns to the surface, deck crew secure it before bottles are opened. Each bottle is drained into pre-labeled containers. No sample is mixed. Order is maintained according to depth sequence. You check turbidity readings against visual clarity. Some samples appear clear, others carry suspended particles. Microscopic analysis will determine composition later. At sea, classification remains provisional. Marine biology is not defined by singular discoveries. It is defined by accumulation. One station contributes a small data set. Multiple stations create patterns. Patterns suggest processes. The first deployment concludes without complication. Equipment is rinsed, bottles are refilled for the next station. Data logs are reviewed for anomalies. The ocean around the vessel shows no visible indication of the layers beneath. Surface waves continue without distinction. The research continues, station by station. There is no urgency, only sequence. At sea, depth is not just distance below the surface. It is structure. The ocean is arranged vertically in layers defined by temperature, density, salinity, and light penetration. A marine biologist studies this vertical architecture before interpreting any biological data. Surface waters form the upper mixed layer. Wind and wave action distribute heat relatively evenly here. Sunlight penetrates this zone, allowing photosynthesis to occur. Phytoplankton convert light energy into chemical energy, forming the base of marine food webs. Oxygen concentrations are generally higher near the surface due to atmospheric exchange. Below this layer lies the thermocline. Temperature begins to decrease more rapidly with depth. The gradient can be sharp, sometimes occurring within tens of meters. This boundary influences nutrient distribution and organism movement. Many species remain above or below the thermocline depending on metabolic needs. You examine the temperature profile displayed on the screen. The line slopes gradually at first, then steepens. The thermocline is clearly defined today. This suggests relatively stable stratification. Surface mixing has not disrupted the vertical gradient. Beneath the thermocline, temperature continues to decline but more slowly. Light intensity decreases significantly. Photosynthesis becomes limited and eventually ceases. This transition marks the boundary between the euphotic zone and deeper waters. The euphotic zone extends only as far as sunlight can penetrate effectively. In clear tropical waters, this may reach over 100 meters. In coastal or turbid regions, it may be much shallower. Productivity depends on both light availability and nutrient supply. You record chlorophyll fluorescence readings from the CTD data stream. Elevated fluorescence can indicate phytoplankton concentration. Peaks often appear near the base of the mixed layer, where nutrients from deeper water meet sufficient light for growth. Below the euphotic zone lies the mesopelagic layer. Light diminishes to near darkness. Many organisms here exhibit vertical migration. They ascend towards surface waters at night to feed and descend during daylight hours. This movement plays a role in carbon transfer between layers. Pressure increases steadily with depth. Approximately 1 atmosphere is added for every 10 meters. At 1,000 meters, pressure exceeds 100 atmospheres. Organisms adapted to these conditions possess specialized cellular structures that resist compression. You observe the pressure reading as it climbs during descent. The instrument casing is engineered to withstand these forces. Sensors must function despite compression that would deform unprotected equipment. Salinity also contributes to density. Small variations influence water, mass formation, and circulation. In polar regions, salt rejection during sea ice formation increases salinity and density, causing water to sink and drive deep ocean currents. Marine biologists interpret biological samples within this physical framework. Species distribution is not random. It correlates with temperature ranges, oxygen availability, nutrient gradients, and pressure tolerance. Oxygen minimum zones often develop in mid-water layers, where decomposition consumes available oxygen faster than it can be replenished. These zones shape species composition. Some organisms avoid them, others tolerate low oxygen conditions. You compare oxygen concentration data against depth. A slight decrease appears at mid-depth today. This may indicate localized respiration patterns or limited mixing. Further analysis will determine whether this is a persistent feature. The bathypelagic zone begins where complete darkness dominates. Below roughly 1,000 meters, sunlight does not penetrate. Energy sources shift. Organic matter from surface waters sinks gradually as marine snow. In certain regions, hydrothermal vents provide chemical energy independent of sunlight. Mapping these layers allows marine biologists to contextualize observations. A plankton sample collected at 50 meters cannot be interpreted without understanding the surrounding physical structure. Likewise, a deep water organism is shaped by pressure and temperature constraints unique to its environment. The ocean is not a single uniform body. It is a layered system connected through circulation patterns that operate on timescales ranging from hours to centuries. Surface currents transport heat across basins. Deep currents redistribute dense water formed in polar regions. You review previous station profiles stored in the onboard database. Comparisons reveal subtle differences in thermocline depth and salinity gradients. These variations may reflect seasonal change or regional circulation patterns. In marine biology, patterns emerge gradually. One profile offers a snapshot. Multiple profiles across distances and timeframes reveal trends. Data accumulation allows interpretation without assumption. The vessel approaches the next station. Another vertical profile will be recorded. Over the course of the expedition, dozens of such profiles will form a structured map of the water column. There is no dramatic shift in the sea's appearance from above. Waves move consistently across the surface. The vertical complexity remains invisible without instrumentation. You prepare for the next deployment. Mapping continues, layer by layer. Marine biology at sea rarely exists as an isolated effort. Individual expeditions are components of institutional research programs that extend across years, sometimes decades. The vessel you are aboard is not operating independently. It follows a predefined scientific framework shaped by funding agencies, universities, international research consortia, and governmental monitoring programs. Long-term observation is central to ocean science. The ocean changes slowly, often beyond the scale of a single expedition. Temperature trends emerge over years. Oxygen distribution shifts across seasons. Biological communities respond gradually to alterations in chemistry and circulation. Because of this, repeated sampling along identical transects is essential. You review the expedition documentation stored in the onboard database. The current cruise revisits a series of coordinates that have been sampled regularly for over 15 years. Each station has a numerical designation tied to historical records. The depth profile collected today will later be compared to profiles collected under similar seasonal conditions in previous cycles. Institutional consistency governs methodology. The same sampling depths are maintained whenever possible. Identical mesh sizes are used in plankton nets. Filtration volumes remain standardized. Even minor procedural deviations can introduce inconsistencies that complicate long-term comparison. Marine research institutions maintain archived datasets accessible to collaborating scientists worldwide. Temperature curves from previous decades can be overlaid with current measurements. Nutrient trends can be plotted across multi-year timelines. Biological abundance can be assessed in relation to environmental variability. The vessel's route reflects this continuity. Rather than selecting visually interesting locations, it follows predefined transects aligned with monitoring objectives. These transects may cross continental shelves, open ocean gyres, or upwelling zones. Each region contributes distinct data points to larger oceanographic models. Funding structures shape mission duration and scope. Grants determine the length of the cruise and the range of instrumentation deployed. Research proposals submitted months earlier define specific objectives, measuring carbon flux, tracking plankton bloom variability, mapping oxygen minimum zones. You examine the cruise plan summary again. It outlines hypotheses without assuming conclusions. The mission is designed to gather evidence rather than confirm expectations. Observations will be compared against predictive models built from satellite data and previous in situ sampling. International collaboration is often embedded within these missions. Ocean basins do not align with national borders. Data from multiple research vessels operating in different regions are integrated into global databases. Shared methodology allows for cross-comparison between hemispheres and ocean basins. Marine biology is therefore cumulative. A single station sampled today may seem routine. Its significance increases when placed within a time series dataset spanning years. Small deviations in salinity or oxygen concentration may indicate larger systemic shifts only visible through repeated measurement. Institutional missions also include quality control standards. Calibration schedules are defined in advance. Sensor drift is documented carefully. When equipment is upgraded, overlap sampling may occur to ensure continuity between old and new instruments. You open archived files from an earlier expedition conducted a decade ago. Thermocline depth appears slightly shallower in recent measurements compared to older profiles. Whether this difference reflects long-term warming or short-term variability requires statistical evaluation across multiple stations. The research vessel functions as a moving laboratory within this broader institutional network. Data gathered on board will later be integrated with satellite imagery, atmospheric measurements, and climate modeling outputs. Marine biology does not operate in isolation from other scientific disciplines. Training of early career researchers is also embedded within institutional missions. Graduate students on board learn standardized procedures. Field notes are reviewed by senior scientists. Documentation practices are emphasized to preserve methodological rigor across generations of researchers. Long-term missions sometimes include autonomous instruments deployed for extended monitoring. Moorings equipped with sensors may remain anchored for months, recording continuous data. During subsequent cruises, these instruments are retrieved and replaced. Their datasets fill gaps between discrete vessel-based sampling intervals. You confirm that one such mooring is scheduled for recovery later in the expedition. Its sensors have been recording temperature and oxygen levels at fixed depths continuously since the previous deployment. Institutional marine biology emphasizes patience. Trends may take years to clarify. Data must be archived meticulously to remain usable decades later. Preservation of sample integrity and metadata accuracy ensures that future researchers can reinterpret datasets using advanced analytical techniques not yet developed. The current mission, therefore, is not self-contained. It contributes a segment to a structured, multi-year observation program designed to track ocean dynamics with precision. The vessel continues along its assigned transect. Life aboard a research vessel is structured around stations, data cycles, and maintenance intervals. Time is measured less by hours and more by sampling sequences. Marine research does not follow a typical day and night rhythm. Operations continue according to weather windows and deployment schedules. A standard rotation divides the scientific team into shifts. 12-hour cycles are common. While one team monitors instruments and processes samples, another rests in narrow cabins below deck. Rest periods are functional, not leisurely. The vessel remains in motion regardless of the hour. You begin your shift before the first station of the cycle. Instrument checks precede deployment. Laptops are powered on. Data acquisition software initializes. Calibration logs are reviewed. Any deviation from expected baseline readings must be identified before sampling begins. The deck crew prepares equipment simultaneously. Communication between scientific staff and vessel operators remains direct and concise. Coordinates are confirmed. Speed is reduced as the vessel approaches the station marker. During deployment intervals, activity narrows to observation. CTD readings are monitored continuously. Descent rate is adjusted if turbulence is detected. Depth targets are confirmed aloud to ensure alignment between lab and deck. Between deployments, sample processing begins immediately. Water collected from discrete depths is filtered for nutrient analysis. Portions are preserved with reagents for later laboratory examination. Labels are cross-checked against digital entries. You record each measurement in duplicate. Digital logs are backed up to external storage devices. Hard copies of station summaries are printed when possible. Redundancy is not optional at sea. Meals occur when schedules permit. The galley serves practical food designed for sustained energy rather than ceremony. Conversations remain technical. Discussions focus on preliminary observations, instrument performance, and environmental conditions. Marine biology at sea involves extended periods of routine. Nets are deployed, retrieved, rinsed, and redeployed. Filters are replaced. Containers are sealed and stored in temperature-controlled compartments. Tasks repeat across stations with minor variation. The vessel's motion becomes background. Stability systems compensate for moderate swells, but slight vibration persists. Equipment is secured accordingly. Metal brackets hold microscopes in place. Storage cabinets lock automatically. You examine a plankton sample under a compact onboard microscope. Movement is subtle. Small crustaceans drift within the water droplet. Identification remains provisional until further analysis ashore. At sea, classification focuses on broad groups rather than detailed taxonomy. Shift changes occur without ceremony. Notes are exchanged between teams. Current conditions, pending analyses, and equipment concerns are summarized efficiently. The outgoing team rests. The incoming team resumes monitoring. Marine research requires physical endurance. Standing for extended periods during processing is common. Gloves protect against chemical reagents. Safety protocols govern handling of preservation fluids. Environmental conditions influence scheduling. Strong winds may delay net deployment. Heavy swells can alter descent angles. Adjustments are made calmly. Contingency plans are part of the crew's design. You review nutrient analysis from earlier stations. Nitrate concentrations appear elevated compared to historical averages. Interpretation will require comparison across multiple stations. No conclusions are drawn prematurely. The vessel's bridge maintains continuous navigation oversight. Depth charts and sonar readings ensure safe passage over variable seafloor terrain. Scientific activity integrates with navigational constraints. Even during rest periods, the ocean remains active. Currents shift gradually. Biological processes continue, independent of observation. The research vessel serves as a temporary platform within a much larger system. Daily routine at sea is defined by sequence rather than novelty. Equipment preparation, deployment, retrieval, processing, logging, and reset. This pattern repeats across the duration of the expedition. You secure filtered samples in a refrigerated compartment. Temperature stability preserves chemical integrity until onshore analysis. Every container is labeled with station number and depth. As the shift progresses, the sky darkens. Artificial lighting replaces natural light on deck. Operations continue without change in procedure. Marine biology at sea is not driven by spectacle. It is sustained by repetition and accuracy. Another station approaches. Preparation begins again. Marine biology at sea depends on controlled sampling. Observation alone is insufficient. Water must be collected, filtered, preserved, and measured in ways that allow later analysis under laboratory conditions. Every method used on board is designed to isolate specific variables without contaminating the broader dataset. The CTD rosette remains the central instrument for vertical profiling. As it descends, sensors continuously transmit conductivity, temperature, depth, dissolved oxygen, and sometimes fluorescence. These readings form the physical framework within which biological interpretation occurs. Around the circular metal frame, Niskin bottles are mounted at equal intervals. Each bottle remains open during descent. At pre-selected depths, electronic triggers release internal springs that close the caps simultaneously at both ends, trapping water from that specific layer. The sequence of closure is predetermined. You verify the firing sequence before deployment. Depth markers correspond to the sampling plan. Surface, thermocline boundary, mid-water column, and near-bottom samples are collected systematically. No bottle is closed randomly. Once retrieved, the rosette is secured on deck. Bottles are opened one by one. Water flows into labeled containers under gravity. Gloves are worn to prevent contamination. Tubing is rinsed with sample water before collection begins. For nutrient analysis, subsamples are filtered through fine membranes. Filtration removes particulates, while allowing dissolved compounds to pass through. Nitrate, phosphate, and silicate concentrations are measured later using spectrophotometric techniques in shore-based laboratories. You measure filtration volumes precisely. Pumps draw controlled quantities of water across filters. Flow rates are monitored to avoid rupturing membranes. Each filter is stored in sealed containers for later analysis of particulate organic matter. Plankton sampling requires different tools. A plankton net is deployed vertically or towed horizontally depending on research objectives. The mesh size determines which organisms are retained. Fine mesh collects phytoplankton and microzooplankton. Larger mesh targets macrozooplankton. After retrieval, the cod end of the net contains concentrated organisms suspended in seawater. This concentrate is transferred carefully into sample jars. Preservation solutions may be added to prevent decomposition before analysis. You rinse the net thoroughly from the outside to ensure that organisms trapped along the mesh are washed into the collection chamber. Incomplete rinsing would bias the sample toward larger or stronger swimmers. Sediment sampling requires heavier equipment. A gravity corer or box corer may be deployed to retrieve seafloor material. These devices penetrate soft sediment and capture vertical columns that preserve layering. Sediment layers reveal historical deposition patterns and biological traces. Hydrothermal vent studies involve specialized sampling arms on remotely operated vehicles. These robotic systems collect mineral deposits and associated biological specimens from extreme environments. At depth, pressure-resistant containers maintain structural integrity during ascent. Acoustic instruments supplement physical sampling. Echo sounders detect biomass concentrations by interpreting sound wave reflections. Fish schools, plankton layers, and even density boundaries can be inferred from acoustic backscatter data. You monitor acoustic readings alongside physical sampling. When backscatter intensifies at certain depths, it may indicate biological aggregation. This information informs decisions about additional targeted sampling. Water chemistry analysis extends beyond nutrients. Dissolved carbon measurements contribute to understanding the global carbon cycle. Oxygen concentrations help define respiration rates and biological productivity. Trace metals can indicate pollution or natural mineral sources. All instruments require calibration. Before departure, sensors are tested against known standards. During the expedition, periodic checks ensure that drift has not altered measurement accuracy. Calibration logs are preserved alongside sample data. Sampling must account for contamination risks. Plastic equipment can leach compounds into water samples. Metal surfaces may introduce trace elements. Clean handling protocols reduce interference. Sample containers are rinsed multiple times with collected water before final filling. You log the time between sample retrieval and preservation. Delays can alter chemical composition due to microbial activity. Consistency in handling is critical. Not all sampling is vertical. Horizontal tows capture organisms distributed across surface waters. Surface skimmers collect floating debris and microplastics. These methods broaden the spatial scope of research beyond discrete depth points. Marine biology instrumentation evolves with technology. Autonomous underwater vehicles can conduct transects without tethering. Satellite remote sensing identifies surface chlorophyll concentrations. Data from multiple platforms integrate to form comprehensive models. Yet even with advanced systems, physical presence at sea remains necessary. Instruments require maintenance. Unexpected conditions require human adjustment. Data interpretation often begins on board as patterns emerge. Sampling is not performed for immediate narrative effect. It is performed to construct datasets that withstand scrutiny. Replication across stations increases reliability. Variation across depth profiles informs interpretation. You seal the final container from the current station. Labels are cross-checked once more. Digital entries match handwritten logs. Instruments are rinsed and secured. The process is repeated at the next coordinate. Precision remains consistent. Method precedes interpretation. Marine biology advances through accumulation of carefully gathered measurements. Marine research does not end when a sample is collected. In many ways, collection is only the beginning. Data must be structured, preserved, verified, and organized before interpretation can even begin. Without disciplined documentation, sampling loses scientific value regardless of technical precision. Every station produces layered datasets. The CTD generates a continuous vertical profile of conductivity, temperature, depth, dissolved oxygen, and sometimes fluorescence. Niskin bottles capture discrete water samples from selected depths. Plankton nets produce biological concentrates. Acoustic instruments record biomass distribution. Each dataset must be aligned to a single station identifier. You open the onboard data acquisition system. Station number is entered before any files are saved. Depth markers from the CTD are synchronized automatically with the vessel's time server. Time consistency ensures that later comparisons across instruments remain valid. Redundancy is built into the workflow. Primary data are stored on the main workstation. Secondary copies are written simultaneously to an external solid-state drive. At the end of each shift, a third backup may be transferred to a secure onboard server. Data loss at sea is unacceptable. Whether electrical instability or mechanical malfunction must not compromise the dataset. Digital entries are not sufficient alone. A physical station logbook is maintained. Handwritten notes document unexpected conditions. If a sensor displayed brief instability during descent, the timestamp is recorded manually. If the winch paused momentarily at a specific depth, it is written down. Context preserves interpretability. Preliminary onboard analysis provides directional insight. Portable nutrient analyzers process small subsamples to estimate nitrate or phosphate concentration. Dissolved oxygen titrations confirm electronic sensor readings. These preliminary values are not final, but they guide sampling adjustments. You generate a vertical profile graph from the most recent CTD descent. The thermocline depth aligns with earlier stations. Oxygen concentration declines gradually through mid-water. Surface salinity shows slight variation compared to the previous coordinate. These observations are noted without interpretation. Consistency governs the workflow. Data files are named using structured conventions. Date, station number, and instrument type are encoded within file names. Mislabeling even a single file can introduce confusion during post-cruise analysis. Filtering logs are recorded separately. Each membrane filter used for particulate analysis receives a unique code. Volume filtered is entered precisely. Flow rate and time of filtration are documented. Later, mass measurements of dried filters will be compared against these initial entries. You cross-check entries against the station summary sheet. Depth values correspond. Sample container labels match digital records. Any discrepancy is corrected immediately and logged transparently. Overwriting errors without documentation is prohibited. Acoustic data require post-processing even on board. Raw backscatter signals are converted into biomass estimates using calibration coefficients. Noise from vessel movement is filtered digitally. Data are flagged if turbulence interfered with signal clarity. Marine biology onboard analysis remains restrained. Patterns are observed but not concluded. A slight chlorophyll peak at the thermocline may indicate productivity enhancement. Confirmation requires multiple stations and later laboratory validation. Shift transitions include data review. The outgoing team summarizes anomalies. The incoming team verifies that backups were completed. Data continuity across shifts ensures no gap in documentation. Satellite communication may allow partial data transmission to shore-based collaborators. Bandwidth limitations restrict file size. Only essential summaries are transmitted. Complete datasets remain on board until return to port. Metadata accompanies every measurement. Weather conditions, wind speed, sea state, and time of day are recorded. Even if these variables do not appear immediately relevant, they provide context for future interpretation. You review previous station profiles stored in the onboard database. Graph overlays display small spatial variability across the transect. The differences are subtle. Interpretation will require statistical analysis beyond the scope of onboard review. Data logging requires patience. Each measurement must be placed within a structured system. Skipping a step introduces potential ambiguity months later during analysis. Digital timestamps align with GPS coordinates. Geographic precision allows mapping of spatial gradients across the cruise track. Positioning errors are flagged if drift occurred during deployment. Backup drives are stored in separate compartments to prevent simultaneous loss. Physical separation of storage media protects against localized damage. Marine biology depends on disciplined documentation. Interpretation may occur months after collection. Clarity of records determines reliability of conclusions. You close the station file only after confirming all entries are complete. The next deployment begins shortly. Marine research at sea depends as much on operational stability as on scientific method. Equipment functions continuously in a corrosive environment. Salt water accelerates oxidation. Constant vibration affects mechanical tolerances. Maintenance is integrated into daily routine rather than treated as a separate task. After each deployment, the CTD frame is rinsed with fresh water. Salt residue accumulates quickly on metal surfaces. If not removed, it forms crystalline deposits that interfere with moving components and electrical connectors. The rinse procedure follows a fixed sequence. Sensors are sprayed gently to avoid forcing water into sealed housings. Cable entry points are inspected visually. You examine the winch cable for signs of abrasion. Microscopic fraying can expand under tension. The cable carries significant load during deep deployments. Replacement schedules are defined by operational hours rather than visible damage alone. Preventive replacement reduces risk more effectively than reactive repair. Electrical systems are inspected regularly. Moisture intrusion into connectors can distort signal transmission. Silicone seals are checked. Spare connectors are stored in dry containers. Before each major station, continuity tests confirm that sensors are transmitting stable signals. Redundancy governs instrument readiness. Backup temperature probes remain calibrated and stored in shock-resistant cases. If a primary sensor drifts beyond acceptable tolerance, replacement occurs immediately, rather than postponing sampling. Calibration logs document the exchange. Laboratory spaces require similar discipline. Chemical reagents used for sample preservation are stored in sealed compartments. Expiration dates are checked. Volumes are recorded. Spill containment kits remain accessible. Even minor spills are logged to ensure that contamination does not compromise nearby samples. Safety procedures extend beyond equipment care. Deck operations present inherent risks. Steel cables under tension can recoil if released unexpectedly. Personnel wear protective gloves and helmets during deployment. Clear verbal signals coordinate winch movement. Only designated crew members operate heavy machinery. You review the vessel's safety checklist posted near the laboratory entrance. Emergency protocols are displayed clearly. Fire suppression systems are tested weekly. Life raft access points are unobstructed. Evacuation drills occur periodically, even during active research cruises. Weather conditions influence maintenance scheduling. If wind speeds increase beyond defined thresholds, deployment may pause. Equipment is secured with additional restraints. Loose objects are stored. Monitoring continues inside the lab until deck operations resume safely. Battery systems require routine verification. Portable instruments used for field measurements depend on stable power supply. Charging cycles are tracked. Spare batteries are labeled and rotated to prevent uneven degradation. Submersible missions require additional redundancy layers. Independent ballast release mechanisms ensure ascent capability even if primary systems fail. Communication systems operate on separate frequencies. Internal pressure sensors are cross-checked before descent. Hull inspections occur at regular intervals. Even though structural integrity is engineered for extreme pressure, visual checks for microfractures or seal wear remain standard procedure. Documentation records, inspection times, and outcomes. You log maintenance activity in the operations file. Date, time, and component inspected are recorded. Preventive actions are noted even when no defect is found. Documentation supports accountability and traceability. Fire safety extends to laboratory equipment. Heating elements used for sample processing are monitored. Circuits are not overloaded. Extension cables are minimized. Electrical load distribution is calculated to prevent instability. Storage compartments are secured against vessel movement. Glassware is held in padded racks. Heavy equipment is bolted down. Sudden shifts caused by wave impact can dislodge unsecured instruments. Marine biology at sea requires coordination between scientific staff and engineering crew. Mechanical expertise complements research objectives. If hydraulic systems display irregular pressure readings, engineers intervene before sampling resumes. Redundancy also applies to data preservation. Backup drives are stored in separate compartments. At least one copy of critical datasets remains isolated from primary workstations. Physical separation reduces risk of simultaneous damage. You inspect filtration pumps before the next station. Flow rate consistency ensures reliable particulate measurement. Tubing connections are tightened. Spare pump heads are available if wear reduces efficiency. Emergency medical kits are checked regularly. Even minor injuries must be treated promptly to avoid complications during extended missions. Personnel are briefed on safety procedures prior to departure from port. Marine research cruises operate within defined safety margins. Operational limits are respected regardless of sampling opportunity. A promising station is not pursued if environmental conditions exceed safe thresholds. Maintenance tasks may appear repetitive, but they preserve continuity of measurement. Equipment reliability ensures that datasets remain comparable across stations and years. You complete the daily maintenance log entry. Systems remain stable. Deployment readiness is confirmed. The vessel maintains course toward the next coordinate. Not all marine research remains at the surface. Some expeditions require direct observation below the upper layers of the ocean. When remote sensors are insufficient, submersibles or remotely operated vehicles extend the reach of human research into depths where sunlight does not penetrate. The descent is procedural. Before deployment, pressure tolerances are reviewed. Hull integrity is inspected. Communication systems are tested. Battery capacity is confirmed. Descent schedules are calculated based on target depth and anticipated bottom time. You enter the submersible with minimal equipment. Interior space is compact. Control panels line the front section. Screens display external camera feeds, depth readings, temperature data, and pressure indicators. Redundant systems ensure that a single failure does not compromise ascent capability. The support crew secures the submersible to a crane. Once lifted over the side of the vessel, it is lowered gradually into the water. The transition from deck to sea is controlled and deliberate. Surface buoyancy stabilizes the vehicle before descent begins. Descent is measured in meters per minute. Too rapid a drop may strain systems. Too slow, a descent reduces operational time at depth. The balance is calculated before the mission begins. As the submersible sinks below the surface, light diminishes progressively. Within the upper 100 meters, ambient sunlight remains visible. Beyond this zone, illumination shifts toward blue wavelengths. Shadows deepen. You monitor the depth gauge as it increments steadily. 100 meters, 200, 500. Pressure increases predictably. The hull absorbs force evenly. Internal conditions remain stable. The thermocline is crossed during descent. Temperature readings drop sharply over a relatively short vertical distance. Outside the submersible, water density increases slightly. Internal systems compensate automatically. Below 1,000 meters, natural light fades entirely. Artificial illumination becomes necessary. External lamps activate, casting narrow beams into suspended particles drifting in the water column. Marine snow appears within the light cones. Organic debris descends slowly from surface productivity. Each particle represents material that may sustain deep-sea organisms far below. The descent continues without acceleration. Every depth interval is recorded. External cameras transmit continuous footage to the surface vessel. Communication remains stable through tether or acoustic relay systems. You adjust ballast to maintain vertical stability. Subtle corrections prevent unwanted rotation. Orientation is crucial for navigation near seafloor terrain. At greater depths, water temperature approaches near freezing conditions. Despite the cold, hydrostatic pressure dominates environmental constraints. Structural engineering, not thermal insulation, determines survivability. Approaching the seafloor requires precise navigation. Sonar systems map bottom contours. Irregular terrain may include ridges, sediment plains, or hydrothermal formations. Landing is avoided unless sampling requires direct contact. The submersible slows further as depth targets are reached. Thrusters counteract residual momentum. Sediment disturbance must be minimized to preserve visibility and prevent contamination of samples. You observe the seabed through forward cameras. Fine sediment covers wide expanses. Occasionally, structural features interrupt the flat terrain. Biological presence becomes visible within the illuminated field. At depth, movement is subtle. Organisms conserve energy. Many species exhibit slow locomotion adapted to scarce food availability. Light-sensitive creatures retreat from illumination beams. The descent phase concludes when target depth is stabilized. Systems checks confirm pressure equilibrium and operational readiness for data collection. There is no dramatic arrival, only confirmation of depth and initiation of observation. At depth, orientation depends on instrumentation rather than visual reference. Natural light does not reach this zone. External illumination from the submersible defines the limits of visibility. Beyond the beams, darkness remains continuous. Navigation near the seafloor requires coordinated use of sonar, inertial guidance systems, and external camera feeds. Sonar pulses emit acoustic signals that reflect off terrain and objects. The return signals form a contour map displayed in simplified outlines. These outlines guide movement more reliably than visual cues alone. You reduce forward thrust to maintain controlled proximity to the seabed. Thrusters adjust in small increments. Vertical stabilization prevents unintended contact with sediment. Even minor disturbances can create clouds of suspended particles that obscure visibility. Sediment composition varies by region. Some areas consist of fine, loosely packed particles that rise easily when disturbed. Other zones are compacted by geological processes or biological activity. The texture of the seabed influences sampling strategy. Hydrostatic pressure remains constant at operational depth. Internal systems monitor hull integrity continuously. External sensors track temperature, salinity, and chemical anomalies. Data streams to both onboard displays and surface monitoring stations. Marine biologists navigating at depth focus on structural features. Seafloor ridges, fault lines, and vent systems create localized ecosystems. Organisms cluster around energy sources and nutrient availability. You identify a slight elevation in the sonar profile. The structure rises gradually from the surrounding plane. Thrusters shift to maintain parallel alignment. External lights sweep across the formation. Biological activity often increases near geological features. Sessile organisms attach to hard substrates. Mobile species patrol the periphery. The distribution reflects adaptation to microhabitats, shaped by temperature gradients and chemical output. At hydrothermal vent sites, chemical plumes rise from fissures in the seabed. These vents release mineral-rich fluids heated by geothermal processes. Specialized bacteria utilize chemical energy through chemosynthesis. This process supports entire ecosystems independent of sunlight. You maintain a steady distance from vent openings. Temperature fluctuations near active vents can be extreme. Proximity sensors monitor safe operational range. Sampling arms extend only when conditions stabilize. Navigation is deliberate and slow. Speed is secondary to precision. Cameras adjust focus as organisms enter the illuminated field. Video recordings capture long sequences without abrupt movement. Some species exhibit bioluminescence. When disturbed by light or motion, they emit faint glows. The phenomenon serves communication or defense functions, depending on species. Illumination patterns vary from brief flashes to sustained radiance. You log coordinates for each observed cluster of organisms. Mapping distribution patterns allows correlation with chemical and thermal measurements. Later analysis will compare biological density against environmental variables. Acoustic instruments supplement visual navigation. Changes in backscatter intensity may indicate schools of mid-water organisms above the seafloor. These readings guide vertical adjustments when necessary. Battery life imposes operational limits. Power consumption is monitored continuously. Efficient movement conserves energy for sampling tasks rather than extended transit. Occasionally, larger organisms enter the light field. Deep-sea fish move slowly, conserving metabolic energy. Some display elongated appendages adapted to low-light environments. Observations remain descriptive rather than interpretive during initial recording. You adjust the submersible's angle slightly to avoid uneven terrain. Mechanical arms remain secured until sampling coordinates are confirmed. Stability is prioritized over proximity. Communication with the surface vessel remains concise. Depth, heading, environmental anomalies, and sample readiness are reported at defined intervals. Silence between updates is normal. The deep-sea environment is structured by gradients rather than dramatic features. Temperature shifts, mineral plumes, and sediment composition define ecological boundaries. Navigation aligns with these invisible parameters. Observation continues methodically. Movement remains measured. At operational depth, exploration is governed by control, not curiosity. Direct observation at depth differs from surface sampling. Here, organisms are encountered within their native environment rather than extracted into containers. Movement is slow. Patterns are subtle. Biological density varies across short distances depending on substrate and chemical gradients. Illumination from the submersible defines the observable field. Beyond the beam, darkness absorbs detail. Within the light, suspended particles drift steadily, reflecting minor water movement. Visibility depends on how carefully thrusters are controlled. You stabilize the vehicle several meters above the seabed. Cameras adjust exposure automatically. Recording systems capture continuous footage for later frame-by-frame analysis. Still images supplement video data at key observation points. Sessile organisms often dominate hard substrates. Sponges attach to rocky protrusions. Deep-sea corals extend branching skeletons into passing currents. Their growth is measured in millimeters per year. Unlike shallow coral reefs, these species do not depend on photosynthesis. They rely on particulate organic matter transported downward from surface productivity. Mobile species move slowly across sediment plains. Sea cucumbers ingest fine particles, extracting organic content before depositing processed sediment behind them. Brittle stars extend arms outward to intercept drifting food. You observe spacing between organisms. Distribution is rarely random. Slight elevation changes can alter current flow, concentrating food particles in localized areas. Chemical gradients near vent systems further structure community layout. Bioluminescent organisms appear intermittently. Some emit brief flashes when disturbed. Others display steady glow along appendages. The mechanism relies on chemical reactions involving luciferin and luciferase compounds. Light production requires minimal energy relative to metabolic constraints at depth. Predatory species are adapted for low-resource environments. Anglerfish utilize bioluminescent lures to attract prey within short visual ranges. Their skeletal structures reduce density to conserve energy expenditure. Teeth appear disproportionate to body size, maximizing feeding opportunity when encounters are rare. You maintain consistent lighting to avoid unnecessary disturbance. Sudden brightness shifts can alter natural behavior. Continuous observation provides a more accurate record of baseline activity. Near hydrothermal vents, biological density increases significantly. Tube worms cluster around vent openings. Their symbiotic bacteria convert chemical compounds into usable energy. These ecosystems operate independently of solar input, relying entirely on geothermal processes. Temperature readings fluctuate slightly as the submersible moves across vent peripheries. Chemical sensors detect elevated concentrations of dissolved minerals. Biological presence correlates closely with these measurements. Recording equipment documents orientation and movement patterns. Behavioral analysis occurs later. At sea, classification remains preliminary. Focus remains on accurate capture of spatial relationships. You adjust position to observe sediment disturbance patterns created by benthic organisms. Burrows indicate infaunal activity beneath the visible surface. Tracks across sediment reveal feeding routes or migratory movement. Deep-sea ecosystems operate on slower temporal scales. Metabolic rates are reduced compared to surface organisms. Growth and reproduction cycles extend over longer intervals. This pacing influences community stability. Large-scale disturbances are rare but impactful. Submarine landslides, tectonic shifts, or significant temperature anomalies can reshape habitats. Evidence of such events appears as sediment layering differences or abrupt species absence across mapped areas. You log timestamps alongside coordinates for each observation cluster. Later analysis will align biological distribution with recorded physical parameters from CTD and chemical sensors. Observation does not imply intervention. Sampling decisions are made selectively to preserve ecosystem integrity. Collection arms extend only when predefined criteria are met. The submersible remains stable as recording continues. Battery consumption remains within expected range. Surface communication confirms time remaining at operational depth. Biological observation at depth prioritizes documentation over reaction. Patterns are recorded without immediate conclusion. Interpretation follows accumulation of evidence. The environment remains quiet. Movement continues at a measured pace. Deep-sea exploration is defined not only by discovery, but by limitation. Every descent operates within calculated boundaries. Engineering tolerances, energy reserves, communication capacity, and environmental conditions determine the duration and scope of observation. Before bottom operations begin, ascent parameters are already established. Operational depth is selected based on hull rating. Maximum pressure tolerance is not approached casually. Safety margins are maintained consistently below structural thresholds. You monitor internal pressure indicators as a formality rather than concern. The submersible is designed for depths beyond the current target, yet redundancy remains part of protocol. Systems do not operate at maximum capacity unless necessary. Battery reserves define bottom time. Thrusters consume energy during stabilization and maneuvering. Lighting systems require continuous power in complete darkness. Data recording equipment operates throughout the mission. Every watt expended reduces available operational duration. Energy allocation is calculated in advance. A percentage of total battery capacity is reserved exclusively for ascent. This reserve is never compromised. Even if unexpected observations appear, departure timing follows the predefined energy schedule. Communication bandwidth at depth is restricted when acoustic transmission replaces tethered fiber links. Acoustic signals transmit essential telemetry: depth, heading, system status. High-definition video streams may be compressed or buffered. Real-time transmission yields to data integrity. You review remaining operational minutes displayed on the central console. The clock does not dictate urgency, but it defines constraint. Observation sequences are prioritized accordingly. Mechanical reach is also limited. Robotic arms extend only within specific articulation ranges. Excessive extension introduces stress to joint assemblies. Precision sampling requires alignment rather than force. If terrain orientation exceeds safe angles, sampling is postponed. Environmental conditions at the surface influence deep operations. Strong surface currents alter tether tension in remotely operated vehicles. Even slight drift in the support vessel's position can affect submersible stability below. Weather forecasts are monitored continuously by the bridge crew. If storm systems approach, recovery schedules are adjusted. Ascent may occur earlier than planned to avoid hazardous retrieval conditions. Temperature gradients impose equipment stress. Rapid thermal transitions during descent and ascent can affect material expansion rates. Engineers account for this through controlled ascent speeds. Gradual vertical movement minimizes thermal shock. Sediment disturbance presents operational limitation. If thruster output is excessive near the seabed, suspended particles obscure camera visibility. Observation quality decreases immediately. To preserve clarity, maneuvering remains deliberate and minimal. Pressure impacts not only structure but instrumentation sensitivity. Sensor calibration shifts slightly under extreme hydrostatic load. Real-time correction algorithms compensate for predictable deviations. Post-mission recalibration verifies measurement stability. You observe that ascent planning has already begun internally. Even while recording continues, countdown to retrieval remains visible. Curiosity does not override boundary. Operational limits extend to human factors. Crew endurance defines cognitive sharpness. Extended missions require rotation schedules. Even submersible pilots follow strict duty time regulations to maintain performance reliability. Biological sampling itself is constrained. Not every organism observed can be collected. Ethical guidelines govern extraction. Rare species are documented visually unless collection is justified scientifically. Preservation of ecosystem integrity guides decision-making. Navigation limits horizontal coverage. Deep-sea exploration is spatially narrow relative to ocean scale. A single descent surveys only a limited radius. Broader mapping requires repeated dives across multiple coordinates. You compare sonar mapping data with mission objectives. Only designated sectors are prioritized for direct observation. Time does not permit exhaustive coverage. Emergency systems remain in passive readiness. Independent ballast release mechanisms ensure buoyant ascent if primary propulsion fails. Backup lighting systems activate automatically if main circuits interrupt. Noise management also defines limitation. Excessive thruster output can disturb sensitive species and distort acoustic measurements. Quiet maneuvering preserves environmental baseline conditions. The submersible operates as a contained system within extreme surroundings. Every parameter, depth, time, power, communication, exists within defined tolerances. These boundaries ensure return capability. You confirm that bottom time approaches its predetermined limit. Remaining tasks are concluded sequentially. Cameras record final sweeps of the immediate terrain. Coordinates are logged. Sampling arms retract fully. Ascent begins not because exploration has ended, but because constraint defines conclusion. Thrusters adjust orientation upward. Vertical movement resumes. In the absence of sunlight, energy does not disappear. It changes form. Below the euphotic zone, photosynthesis ceases, yet biological activity persists. Bioluminescence becomes one of the most visible manifestations of life in this environment. Bioluminescence is the production of light by living organisms through chemical reaction. The process typically involves a light-emitting molecule known as luciferin and an enzyme called luciferase. When these compounds react in the presence of oxygen, photons are released. The reaction generates light with minimal heat production, making it metabolically efficient. You observe faint pulses in the water column as the submersible's external lights dim slightly to reduce interference. Small flashes appear intermittently beyond the primary illumination beam. These flashes are not random. They represent biological responses to mechanical disturbance or environmental stimuli. In the deep ocean, light serves multiple functions. Some organisms use it for communication. Patterns of blinking or sustained glow may signal reproductive readiness or species identification. Other species deploy light defensively. A sudden flash can startle predators or distract them long enough to allow escape. Predatory species also utilize bioluminescence. Certain deep-sea fish possess specialized appendages that emit controlled light. These lures attract prey within short visual range. Because food encounters are infrequent at depth, efficiency in capture is critical. You adjust camera sensitivity to capture subtle glows without overexposure. Many species emit blue or green wavelengths, which travel more effectively through seawater. The spectral properties of emitted light align with the absorption characteristics of the environment. Bioluminescence is not limited to fish. Planktonic organisms in the mesopelagic layer also emit light. When disturbed by movement, microscopic dinoflagellates produce brief flashes. This phenomenon, sometimes visible at the ocean surface as glowing waves, originates from similar biochemical processes. At depth, the intensity is weaker, but distribution remains widespread. Studies estimate that a majority of deep-sea species exhibit some form of bioluminescence during part of their life cycle. The trait evolved independently multiple times, suggesting strong adaptive value. You record the spatial distribution of visible flashes relative to current direction. Currents influence how organisms encounter mechanical disturbance. Concentrations of flashing may indicate areas of higher plankton density. Energy sources at depth differ fundamentally from those near the surface. Organic matter descends gradually from upper layers as particulate detritus. This material sustains heterotrophic organisms. However, in certain regions, chemical energy supports life independent of surface productivity. Hydrothermal vent systems exemplify this process. Chemosynthetic bacteria oxidize reduced chemical compounds such as hydrogen sulfide. These reactions release energy used to fix carbon into organic molecules. Larger organisms form symbiotic relationships with these bacteria, deriving nutrition indirectly from geothermal processes. You observe faint shimmering near vent plumes. The glow is not bioluminescent in origin, but results from mineral-rich fluids interacting with seawater. True bioluminescence remains organism-driven and enzymatic. The distribution of bioluminescent species varies by depth zone. In the mesopelagic layer, light production supports vertical migration patterns. In the bathypelagic zone, it aids prey detection and predator avoidance. In abyssal plains, where food availability is minimal, light emission may be rarer but still present among specialized taxa. Physiological control over light emission differs among species. Some organisms produce continuous glow through bacterial symbionts housed in specialized organs. Others generate rapid flashes through neural control of enzymatic reactions. Energy efficiency remains critical in low-resource environments. You reduce thruster output to minimize disturbance. When mechanical vibration decreases, flashes become less frequent. The surrounding darkness returns to near uniformity. Bioluminescence also contributes to camouflage. Counter-illumination strategies allow certain species to match the faint, downwelling light from above, rendering them less visible to predators below. Even in low-light conditions, relative contrast determines visibility. The biochemical pathways underlying light production are studied extensively in laboratory settings, yet direct observation at depth provides ecological context. Laboratory replication cannot fully simulate pressure, temperature, and ambient darkness simultaneously. You log timestamps corresponding to observed luminescent events. Later, these entries may align with acoustic data to identify vertical distribution patterns. Light in the deep ocean is not decorative, it is functional. It replaces sunlight as a medium of interaction. It defines predation strategies, communication signals, and defensive responses. As observation continues, flashes appear sporadically within the illuminated field. The majority remain brief and localized. Patterns emerge slowly. Energy persists at depth through transformation rather than abundance. Bioluminescence is one of its expressions. Hydrothermal vent systems represent one of the most structurally distinct environments in the deep ocean. Unlike surrounding sediment plains, vent fields are shaped by geological activity. They form where tectonic plates diverge or where magma chambers heat seawater that has penetrated fractures in the oceanic crust. Cold seawater seeps downward through cracks in the seafloor. As it approaches underlying magma, it is heated to temperatures that may exceed 300 degrees Celsius. During this process, the water dissolves minerals from surrounding rock. The heated, mineral-rich fluid then rises and exits through chimney-like structures on the seabed. You stabilize the submersible at a safe distance from a vent structure. Sonar confirms uneven terrain. External cameras reveal vertical formations, rising several meters above the surrounding substrate. These chimneys are often referred to as black smokers when the expelled fluid appears dark due to suspended metal sulfides. The fluid temperature at the point of emission can be extreme, yet surrounding seawater remains near freezing. Rapid mixing creates steep temperature gradients within small spatial scales. This gradient defines ecological boundaries around the vent. Hydrothermal vents support biological communities independent of sunlight. Energy originates from chemical reactions rather than photosynthesis. Chemosynthetic bacteria oxidize reduced compounds such as hydrogen sulfide, methane, or iron. Through these reactions, carbon dioxide is converted into organic matter. You monitor temperature and chemical sensors as readings fluctuate slightly with proximity to the vent plume. Elevated hydrogen sulfide concentrations correlate with visible biological clustering. Large tube worms are among the most recognizable vent organisms. These animals lack a conventional digestive tract. Instead, they host symbiotic bacteria within specialized internal tissues. The bacteria perform chemosynthesis, providing nutrients to the host organism. In exchange, the host supplies access to chemical substrates and oxygen. Clusters of bivalves, crustaceans, and specialized shrimp inhabit the periphery of vent emissions. Each species occupies a specific range within the thermal and chemical gradient. Too close to the vent, temperature exceeds tolerance. Too far away, chemical energy declines. You adjust lighting intensity to reduce disturbance. Certain vent shrimp possess modified photoreceptors sensitive not to visible light, but to faint infrared radiation emitted by vent plumes. Their visual systems are adapted to detect thermal signatures rather than ambient light. Mineral deposition shapes vent structures over time. As heated fluids contact cold seawater, dissolved metals precipitate, layers accumulate, forming chimney walls composed of sulfide minerals. Structural collapse can occur as vent activity fluctuates. Vent fields are not permanent. Geological shifts may close one vent while opening another nearby. Biological communities must respond to these changes. Succession patterns occur as new vents become active and old ones diminish. You log vent location coordinates and structural dimensions. Mapping vent fields contributes to understanding plate tectonics as well as ecological distribution. The physical and biological systems are interdependent. Hydrothermal vent ecosystems challenged earlier assumptions that sunlight was necessary for complex life. Their discovery expanded understanding of energy pathways capable of supporting biological communities. The chemical gradients present at vents provide stable energy flux independent of surface productivity. Water chemistry near vents differs significantly from surrounding seawater. Metal concentrations increase. pH levels may shift. Microbial communities specialize in metabolizing available compounds. Genetic studies reveal adaptations unique to these environments. Sampling near vent systems requires precision. Robotic arms extend only when turbulence from the plume subsides. Containers designed to maintain pressure integrity capture specimens with minimal structural distortion during ascent. You maintain a cautious distance from active emission points. Rapid temperature variation can affect equipment sensors. Thermal shielding protects exposed surfaces. Vent fields are often distributed along mid-ocean ridges spanning thousands of kilometers. Yet individual vent sites remain localized. A submersible descent observes only a small fraction of the total system. The ecological density around vents contrasts sharply with surrounding abyssal plains. Organism abundance increases within narrow spatial bands defined by chemical concentration gradients. You record continuous video as biological clusters shift subtly in response to plume flow. Movement remains measured. No sudden migrations occur. Hydrothermal vent systems illustrate how geological energy becomes biological structure. Heat from Earth's interior is converted indirectly into organic matter through microbial metabolism. The submersible remains stationary as observation continues. Data logging proceeds alongside visual recording. Vent activity persists according to geological rhythm. In the deep ocean, energy transfer follows pathways shaped by scarcity rather than abundance. Unlike surface ecosystems sustained by continuous photosynthesis, deep-sea food webs depend on limited inputs. Organic matter descends slowly from upper layers. Chemical energy supports localized systems near vents. Every trophic interaction reflects constrained availability. Primary production in surface waters forms the base of most marine food webs. Phytoplankton convert light into organic compounds. A portion of this material is consumed near the surface. Another portion sinks gradually as particulate organic matter. This descending material is often referred to as marine snow. You observe suspended particles illuminated in the submersible's external lights. These fragments consist of decomposing plankton, fecal pellets, mucus aggregates, and microscopic debris. As they descend, microorganisms colonize and partially decompose them, reducing nutrient content progressively with depth. By the time marine snow reaches bathypelagic depths, only a fraction of original surface productivity remains. Organisms adapted to these conditions evolve low metabolic rates and energy-efficient feeding strategies. Deposit feeders dominate abyssal plains. Sea cucumbers ingest sediment continuously, extracting residual organic compounds. Polychaete worms burrow beneath the surface, processing detritus trapped within sediment layers. Energy extraction efficiency is critical for survival. Predatory relationships exist, but operate at reduced frequency compared to shallow ecosystems. Deep-sea fish often exhibit opportunistic feeding behavior. Encounters with prey may be infrequent, requiring anatomical adaptations such as expandable stomachs or elongated jaws. You review acoustic backscatter data collected during descent. Midwater scattering layers indicate vertical migratory organisms. These layers shift upward during night hours and descend during daylight. This daily vertical migration transports organic carbon between depth zones. In the mesopelagic zone, zooplankton and small fish consume phytoplankton and smaller organisms. These midwater species act as intermediaries between surface productivity and deeper consumers. When they die or excrete waste, material continues downward. Chemosynthetic ecosystems at hydrothermal vents form separate but interconnected food webs. Primary production occurs through bacterial oxidation of reduced chemical compounds. Tube worms, vent mussels, and crustaceans derive nutrition directly or indirectly from these bacteria. You compare the structural differences between vent-associated communities and surrounding abyssal plains. Vent food webs are denser and more localized. Abyssal food webs are diffuse and widespread. Scavengers also play a critical role. When large organisms die at depth, their remains create localized nutrient pulses. Whale foals, for example, introduce substantial organic material into otherwise nutrient-poor environments. Successional communities develop around such events, gradually decomposing tissue and bone over extended periods. Food web complexity increases with environmental heterogeneity. Seamounts, ridges, and trenches create microhabitats that support distinct species assemblages. Structural variation allows for niche differentiation even within resource-limited systems. You log observed feeding interactions. A benthic fish pauses near a deposit-feeding invertebrate. A crustacean scavenges particulate debris near vent outflows. These interactions occur slowly, without rapid pursuit. Energy transfer efficiency is lower at depth due to limited input. As a result, biomass density decreases with increasing depth. Organisms invest in longevity rather than rapid reproduction. Growth rates are slower. Population turnover occurs over extended timescales. Stable isotope analysis, performed later in shore-based laboratories, will trace energy pathways through these communities. Ratios of carbon and nitrogen isotopes reveal trophic positions and resource origins. At sea, such relationships are inferred based on observation and sampling. Marine food webs at depth illustrate resilience through adaptation. Scarcity shapes morphology and behavior. Feeding structures maximize capture efficiency. Metabolic processes conserve energy. You observe subtle patterns in organism spacing relative to current direction. Even weak currents transport marine snow. Orientation toward flow increases feeding opportunity for sessile organisms. Unlike surface ecosystems characterized by seasonal blooms and rapid turnover, deep-sea food webs exhibit relative temporal stability. Fluctuations occur but remain moderated by slow input rates and gradual decomposition. The submersible maintains steady position as documentation continues. Food-web interactions proceed without disturbance. Energy in the deep ocean moves through constrained channels, redistributed gradually across trophic levels. The structure remains functional despite limitation. Pressure increases predictably with depth. For every 10 meters of descent, approximately 1 additional atmosphere of pressure is added. At 1,000 meters, pressure exceeds 100 atmospheres. In deeper zones, it rises far beyond that threshold. For organisms inhabiting these environments, pressure is not an extreme condition. It is the baseline. Adaptation to hydrostatic pressure influences cellular structure, enzyme function, membrane composition, and skeletal formation. Organisms that live permanently at depth are described as piezophilic, meaning pressure-loving. Their physiological systems operate optimally under conditions that would compromise shallow water species. You monitor depth indicators as the submersible remains stable above the seafloor. External pressure readings remain constant. Inside the hull, internal pressure is maintained at near surface levels. The structural difference between inside and outside illustrates the engineering required for human exploration. Biological adaptation achieves similar resilience through molecular modification rather than mechanical reinforcement. Cell membranes in deep-sea organisms contain higher proportions of unsaturated fatty acids. This composition preserves membrane fluidity under compression. Without such adjustment, membrane rigidity would impair transport processes across cellular boundaries. Enzymes that catalyze metabolic reactions must also remain functional under pressure. Protein folding structures differ slightly from shallow water analogues. These structural modifications prevent denaturation and preserve reaction efficiency. You observe a deep-sea fish moving slowly within the illuminated field. Its body appears elongated and less densely muscled than many shallow water species. Skeletal structures in some deep-sea organisms are reduced in mineralization. High mineral density is not required for buoyancy control in stable pressure conditions. Buoyancy regulation differs at depth. Gas-filled swim bladders, common among shallow water fish, are absent in many deep-sea species. Gas compresses under pressure, making such structures inefficient. Instead, buoyancy may be achieved through lipid storage or reduced skeletal density. Invertebrates exhibit additional adaptations. Crustaceans possess flexible exoskeletons capable of tolerating compression without fracture. Deep-sea amphipods often display thickened carapaces combined with specialized joint structures to distribute pressure evenly. You review sediment samples containing burrowing organisms. These species experience relatively stable pressure conditions, but must tolerate chemical gradients within sediment layers. Adaptation includes resistance to low oxygen and high sulfide concentrations, in addition to pressure tolerance. Reproductive strategies also reflect pressure adaptation. Some deep-sea species produce fewer offspring with extended developmental periods. Slow growth and longevity compensate for limited resource availability and stable environmental conditions. Rapid vertical movement between pressure zones is rare among permanent deep-sea residents. However, vertically migrating species possess biochemical flexibility, allowing short-term tolerance of pressure variation. These species adjust membrane composition dynamically across depth transitions. You log environmental parameters as documentation continues. Temperature at this depth remains near freezing. Combined with high pressure, this environment would disrupt many shallow water metabolic pathways. Yet deep-sea organisms operate within these parameters as normal. Laboratory studies of piezophilic bacteria demonstrate growth rates optimized under pressure conditions, replicating deep-sea environments. When returned to surface pressure, their metabolic efficiency decreases significantly. Adaptation is therefore not merely tolerance but specialization. Hydrothermal vent organisms combine pressure adaptation with thermal tolerance. Despite extreme heat at vent emissions, surrounding water remains cold. Organisms occupy narrow bands where temperature and pressure conditions intersect within survivable ranges. You adjust submersible lighting slightly to examine structural detail on a benthic organism. Movement remains measured. Tissue structure appears intact without collapse under surrounding pressure. Human exploration requires structural shielding to withstand these forces. Deep-sea life achieves equilibrium through biochemical architecture. Pressure influences not only physiology, but ecological distribution. Species boundaries often align with depth-related pressure thresholds. Transitional zones between bathypelagic and abyssal depths correspond to changes in community composition. The submersible remains steady as recording continues. Pressure readings remain constant. Biological activity persists within defined parameters. Adaptation to pressure is not visible as spectacle. It is embedded within molecular structure and anatomical form. Life at depth functions not in defiance of pressure, but in accordance with it. Ascent begins according to schedule, not according to emotion. Operational time at depth has reached its predetermined limit. Power reserves remain within safe margins. Data recording systems confirm final logs before vertical movement resumes. You adjust ballast and thruster orientation. The submersible tilts slightly upward. Forward motion ceases. Vertical propulsion increases gradually. Rapid ascent is avoided to maintain structural stability and minimize sediment disturbance. The seabed recedes slowly from view. External lights continue to illuminate suspended particles drifting through the water column. Marine snow rises past the viewport as the vehicle moves upward. Depth indicators decrease incrementally. Pressure readings fall correspondingly. The hull remains stable, engineered to withstand far greater stress than currently applied. Internal systems recalibrate automatically as pressure declines. You monitor ascent rate continuously. Controlled velocity prevents abrupt thermal or mechanical stress. Gradual transition protects sensitive instrumentation. The bathypelagic zone fades behind. Darkness remains dominant until the submersible approaches mid-water depths. Bioluminescent flashes become less frequent as vertical position changes. Acoustic signals from the support vessel strengthen as distance decreases. At mid-water levels, the thermocline is crossed again. Temperature readings increase slightly. Water density shifts. These changes are predictable and logged automatically. You review collected datasets while ascent continues. Video files confirm continuous recording. Chemical sensor data shows stable output. No anomalies appear in structural logs. Surface support crew prepare for retrieval. Communication confirms estimated arrival time. Crane systems are activated in advance. Deck operations coordinate with ascent velocity. Light intensity begins to increase gradually as the submersible approaches shallower depths. Blue wavelengths return first. Suspended particles reflect more ambient illumination. You confirm that sampling arms are secured fully. External equipment is locked in place. Any unsecured component could be damaged during surface retrieval. Ascent continues at a measured rate. The surface boundary approaches not as a dramatic threshold, but as a gradual increase in light penetration and acoustic clarity. The submersible breaks the surface with minimal disturbance. Buoyancy stabilizes the vehicle automatically. External water drains from upper surfaces. The crane lowers hooks into designated attachment points. You remain seated while deck crew secure the submersible. Only when lifting cables are fully tensioned does retrieval proceed. Vertical movement resumes, this time from water to deck. Once secured, hatch protocols follow standard procedure. Internal pressure equalizes. External inspection confirms hull integrity. Ascent is not a conclusion. It is transition from field observation to analytical phase. Return to the surface does not conclude the research cycle. It shifts the focus from observation to consolidation. Samples collected during descent and surface stations now require systematic processing. Data recorded in multiple formats must be aligned, verified, and prepared for later laboratory evaluation. Once the submersible is secured and deck operations stabilize, sample containers are transferred carefully to the laboratory space. Temperature-sensitive materials are moved first. Preservation timing is logged precisely. Even minor delay can alter chemical composition through microbial activity. You inspect each container against the digital station registry. Labels correspond to depth, time, and sampling method. Cross-verification prevents misidentification. No container is opened before confirmation. Water samples designated for nutrient analysis are filtered under controlled conditions. Filtration volumes are measured accurately. Membranes are sealed and stored in refrigerated compartments. Liquid subsamples are transferred into pre-cleaned vials, sometimes preserved with specific reagents depending on the target compound. Dissolved oxygen samples are prepared for later titration confirmation. Chemical fixation halts biological activity within the vial. This ensures that oxygen concentration reflects in situ conditions rather than post-collection alteration. You review particulate samples collected from plankton nets. Concentrates are divided into subsamples to allow multiple analytical approaches later. One portion may be preserved for taxonomic identification. Another may be frozen for genetic sequencing. Each treatment is documented independently. Sediment cores retrieved earlier are stored vertically to preserve stratification. Surface layers remain undisturbed. Sectioning may occur on board or after return to shore, depending on research objectives. Depth intervals are measured in centimeters, each representing potential historical deposition layers. Data consolidation extends beyond physical samples. CTD profiles are exported into structured files compatible with analytical software. Depth intervals are standardized across stations. Outliers are flagged but not removed without justification. You overlay temperature and salinity profiles from multiple stations along the transect. Gradients reveal subtle shifts in thermocline depth. Patterns emerge gradually rather than abruptly. Statistical evaluation will later quantify significance. Acoustic backscatter data are converted into biomass estimates using calibration curves. Corrections for vessel noise are applied. Comparison across stations identifies areas of increased midwater organism density. Chemical sensor data from the submersible are aligned with spatial coordinates. Hydrothermal vent proximity is correlated with temperature anomalies and mineral concentration readings. Biological observations recorded visually are matched with these environmental metrics. Every dataset receives metadata. Instrument calibration time, sensor serial number, operator name, and environmental conditions are attached to each file. These details ensure traceability months or years later when analysis deepens. You verify backup integrity once more. Primary storage, secondary drive, and onboard server copies all contain identical file sizes and timestamps. Data redundancy remains non-negotiable. Preliminary onboard interpretation remains conservative. Elevated nitrate at certain depths may indicate upwelling influence. Reduced oxygen in mid-water may align with respiration zones. However, no definitive conclusion is recorded until full dataset comparison occurs. Marine biology relies on delayed interpretation. Patterns become meaningful when contextualized across time and space. A single station rarely defines a trend. Multiple stations across consistent transects provide structural insight. You begin organizing files into expedition-level directories. Surface sampling, deep-sea descent data, acoustic mapping, sediment retrieval, and vent chemistry each receive categorized storage. Clear structure prevents confusion during post-cruise laboratory work. Quality control protocols require random rechecks. Selected data points are recalculated manually to confirm digital outputs. If discrepancy exceeds acceptable tolerance, further review occurs immediately. Communication with shore-based collaborators may begin at this stage. Summary statistics can be transmitted via satellite link. Detailed files remain on board due to bandwidth limitation. The laboratory space remains steady despite mild vessel movement. Equipment hums quietly. Refrigeration units maintain temperature stability. Freezers preserve biological material at low temperatures to prevent degradation. You finalize the station consolidation report. Depth ranges, instrument readings, sampling methods, and preliminary observations are summarized in neutral language. No interpretive claims appear in this document. Only recorded measurement. The consolidation process continues for each station until the expedition concludes. Repetition ensures uniformity. Uniformity preserves comparability. Data and samples are now structured, stable, and ready for extended analysis ashore. The vessel maintains its course. Marine biological research does not produce immediate conclusions at sea. Its impact unfolds gradually through extended analysis, comparison across years, and integration into larger scientific frameworks. The expedition you have completed represents one segment within a broader continuum of observation. Once samples are transported ashore, laboratory work continues under controlled conditions. Nutrient concentrations are analyzed using spectrophotometric instruments, calibrated with precision standards. Genetic material extracted from plankton samples undergoes sequencing to identify species composition beyond visual classification. Sediment cores are sectioned carefully, each layer representing potential historical environmental conditions. You review archive datasets in preparation for comparative analysis. Historical thermocline depth, oxygen concentration, and salinity gradients are plotted alongside the most recent measurements. Differences appear subtle at first glance. Statistical modeling determines whether variation exceeds natural seasonal fluctuation. Marine biology increasingly intersects with climate science. Long-term warming trends in surface waters influence stratification patterns. Changes in stratification alter nutrient upwelling, which affects primary productivity. These cascading effects propagate through food webs over extended timescales. Carbon cycling represents another focus of long-term impact. Measurements of dissolved inorganic carbon and particulate organic matter contribute to global carbon budget models. The ocean acts as a significant carbon sink, absorbing atmospheric carbon dioxide. Variations in absorption efficiency influence global climate regulation. You examine oxygen minimum zone expansion across archived transects. Gradual shifts in oxygen concentration at midwater depths have implications for species distribution. Organisms adapted to narrow oxygen thresholds may shift range or decline in density as gradients change. Data integration requires collaboration across institutions. Oceanographic models combine physical measurements, satellite observations, and biological sampling. Each expedition adds resolution to predictive frameworks used for fisheries management, conservation planning, and climate forecasting. Marine protected areas are sometimes informed by repeated biodiversity surveys. Species distribution data gathered across multiple cruises reveal hotspots of biological richness. Protection strategies rely on evidence accumulated through consistent monitoring rather than single observations. You compare plankton community composition between expeditions separated by several years. Subtle shifts in species dominance may reflect temperature anomalies or nutrient variability. Interpretation requires caution and extended dataset accumulation. Long-term datasets also reveal stability in certain regions. Some deep-sea ecosystems demonstrate minimal variation across decades. Such stability provides baseline conditions against which change can be measured. Technological advancement enhances long-term impact. Instruments deployed in earlier years may lack resolution available in current sensors. Overlapping measurement periods ensure continuity while integrating improved precision. Marine biological research informs policy indirectly. Fisheries, quotas, environmental regulations, and climate mitigation strategies often rely on oceanographic data trends. However, translation from dataset to policy occurs through layers of analysis and review. You review publication records linked to the transect sampled during the expedition. Previous cruises contributed to peer-reviewed articles examining thermocline variability and nutrient cycling. The current dataset will extend these analyses. Data archiving protocols ensure accessibility. Public repositories allow other researchers to reanalyze datasets using alternative methods. Transparency supports reproducibility and interdisciplinary application. Genomic sequencing of vent organisms may reveal biochemical pathways with industrial or pharmaceutical relevance. Yet such applications emerge only after extensive laboratory evaluation and validation. Long-term research impact is cumulative rather than immediate. The significance of the expedition lies not in dramatic discovery, but in measured contribution to structured observation. You finalize preliminary data organization for transfer to institutional archives. File structures follow standardized templates. Metadata completeness ensures that future researchers understand context without reliance on memory. The vessel's journey concludes at port, but analytical cycles continue for months or years. Marine biology advances through incremental refinement of understanding. Patterns become visible through persistence. The work continues beyond the voyage. Marine biology, viewed from distance, may appear defined by rare descents, specialized equipment, and unusual ecosystems. In practice, the profession is structured around repetition, documentation, analysis, and sustained observation. The visible moments of exploration represent a small fraction of total activity. After return to port, equipment is unloaded systematically. Sensors are recalibrated. Mechanical systems are inspected for wear accumulated during the expedition. Laboratory spaces are cleared. Samples are transferred into institutional facilities where environmental conditions remain stable. You review the crew's summary once more. Station coordinates, instrument logs, chemical readings, and sampling volumes are consolidated into formal reports. These reports follow standardized templates used across institutions. Language remains precise and measured. Weeks may pass before full laboratory analysis is completed. Nutrient assays require controlled chemical processing. Genetic sequencing generates large datasets that must be assembled and interpreted. Sediment core sections undergo imaging and compositional analysis. The profession's tempo remains steady rather than dramatic. Data interpretation proceeds incrementally. Statistical models are applied. Graphs are refined. Anomalies are examined before conclusions are drafted. Marine biologists often divide time between fieldwork and office-based analysis. Field expeditions may occupy only a portion of the year. The remainder involves writing reports, preparing publications, teaching, or planning future missions. You open a dataset collected several years earlier along the same transect. Comparing historical and recent profiles reveals minor shifts in thermocline depth. Determining whether these shifts represent long-term trend requires careful statistical treatment rather than immediate inference. Grant proposals are prepared months before subsequent cruises. Objectives must be defined clearly. Budget allocations are calculated. Equipment upgrades are requested if necessary. Review committees evaluate scientific merit before funding is approved. The profession also involves collaboration across disciplines. Physical oceanographers contribute circulation models. Chemists analyze trace compounds. Ecologists interpret species distribution patterns. Marine biology intersects with multiple scientific domains. Routine tasks occupy significant time. Data cleaning removes transcription errors. Metadata fields are verified. Calibration curves are recalculated. Software scripts are tested repeatedly to ensure reproducibility. You attend a research meeting where preliminary results are discussed among colleagues. Language remains cautious. Observations are framed as potential trends pending further confirmation. Fieldwork resumes in subsequent seasons. Sampling along the same transect may reveal continuity or gradual change. Long-term monitoring defines professional rhythm. The ocean itself does not accelerate. Surface conditions vary with weather, but deep systems evolve slowly. Understanding these systems requires patience aligned with their timescale. You organize laboratory shelves containing archived samples from previous expeditions. Each container carries identifiers linking it to specific coordinates and depths. Years later, some may be reopened for additional analysis using improved techniques. Publication timelines extend months beyond data collection. Manuscripts undergo peer review. Revisions are requested. Clarifications are made. Precision in language mirrors precision in measurement. The profession rarely produces immediate visibility outside scientific circles. Impact accumulates through citation, replication, and integration into broader models. Marine biology does not operate through isolated breakthroughs. It progresses through structured accumulation of observation across time. You review the next expedition planning schedule. Objectives align with previous monitoring goals. Equipment lists are updated. Personnel assignments are confirmed. Between expeditions, teaching responsibilities may fill portions of the calendar. Students learn sampling methodology, data analysis techniques, and field safety procedures. The pace remains measured. Field seasons alternate with analytical seasons. Sampling alternates with writing. Observation alternates with modeling. The ocean remains present but distant during laboratory months. Data on screen represent environments visited earlier. Interpretation continues long after physical return. Marine biology functions according to sustained continuity rather than episodic intensity. The work proceeds.